Now some changes to Fischer projection. How we can modify the Fischer projection or do some conversions in Fischer projection. We have got the idea of Fischer projection. We'll understand when we change or rewrite the Fischer projection whether it will be same molecule or different molecule, whether the configuration is going to be same or it is going to be different. Let us look at that. Now this is the Fischer projection of glyceraldehyde. This Fischer projection, if I rotate by 180 degree along the plane of the paper, what is 180 degree rotation? This whatever is top goes down, whatever is left goes to the right. So H and OH are like this, they have rotated like this. CH2 and CH2 is like this, they have rotated like this. So that's a 180 degree rotation. So this 180 degree rotation, is it going to be the same molecule or different molecule? Let us look at it in this way. A 3D molecule is going to happen. Now, groups in Fischer projection, groups on the horizontal are towards you. These are the groups that are towards you. Groups on the vertical are away from you. So let us assume this is the Fischer projection. So you can see a slight violet color here and a slight green color here. Now let us assume I am doing a 180 degree rotation. So this is the 180 degree rotation. So after the 180 degree rotation, the violet color is OH. After the 180 degree rotation, again the violet color is OH. So this makes this one as H. So previously CHO is here. Now the CHO is here. So the Fischer projection of this molecule is this only, right? So these two are inside. These two are inside. CHO is inside, CH2OH is inside. OH is outside, H is outside. And now OH falls on OH and H falls on H. Maybe it's not clearly visible. This is OH, this is H. This is CHO, this is CH2OH. I've just shaded with different colors. So when I'm making this molecule from this molecule without breaking or making any bonds, I'm just twisting and I'm getting this molecule. If I want to get the original molecule back, I have to do this. So I'm getting the original molecule back. So in the Fischer projection, if I'm rotating by 180 degree, it is same as taking the molecule and rotating by 180 degree along the plane of the board. That means these two are the same. So can I make a concluding statement? A and B are identical. So if I take a Fischer projection and rotate it by 180 degree along the plane of the board. So this is along the plane of the board, that is important. So in this rotation, whatever groups are into the plane of the board are still remaining into the plane of the board. So whatever groups are into the plane of the board, these two are into the plane of the board. After the 180 degree rotation, still they are into the plane of the board. Just top one came to the bottom and bottom group came to the top. But they are inside. Group that is this side came to this side, group that is this side came to this side. But still both of them are outside the plane of the board. So that is a 180 degree rotation and it is allowed in Fischer conversions. So still you get the identical molecule. One more thing that we can do is a 3-group rotation. What is a 3-group rotation? Let us read this way. So this is one Fischer projection. I am keeping one of the group fixed. So hydrogen's position is fixed and interchanging the position of the other groups. What do I mean by this interchange? Look at this. So bromine I am putting in place of iodine. Iodine I am changing to chlorine's position. Chlorine I am changing to bromine's position. So this interchange of 3 groups is called 3-group interchange. Or I am twisting 3 groups holding the other thing common. So now are these two molecules, after 3-group interchange I am getting this. Are these two same or different? Let us see it this way. So I have to hold one of the group fixed. So let us say this group is hydrogen, I am holding one of the group fixed. Now these three to you, they look at 120 degree angle with respect to each other roughly. Now I am holding this hydrogen, I am doing the rotation. So this rotation is to the molecule only, but it is not changing any connections. So that means I can do a 120 degree rotation or a rotation in this. This is a 3-group interchange. Any times I can do a 3-group interchange. I can twist it like this. I can twist any times like this. I am going to get the same molecule. That is what is a 3-group rotation. So 3-group rotation is allowed and it will give the same molecule that is allowed in Fischer projection. How? You can try thinking about the Fischer wedge representation of this molecule. Hydrogen and bromine are inside. Hydrogen, bromine are inside. Iodine, chlorine are outside. Hydrogen, chlorine are inside. Bromine, iodine are outside. So now you have to mentally imagine twisting this molecule into this molecule such that hydrogen and hydrogen, both of them lie inside of the plane. So this is the 3-group rotation, and this 3-group rotation is going to give the same molecule. As you can see from this itself, 3-group rotation is not going to do any change. This broke. So the 3-group rotation is not going to change anything in the molecule, because this is the 4th group. Rotating the 3 groups like this, is not going to change the configuration. But imagine if I have to do a 2-group interchange, then it changes the configuration. To do a 2-group interchange, I have to break this bond and then only twist it. I have to break this bond and then only I can twist it. But 3-group rotation, it is nothing but twisting the whole molecule. Twisting the whole molecule will not cause any change in the configuration. But twisting 2 groups will cause change in the configuration. That is what you have to understand. So that is why 3-group interchanges any number of times, clockwise or anti-clockwise, both will result in the same configuration. So that means on paper in Fischer projection, you can hold any one molecule, rotate the other 3. You can hold this, rotate the other 3. You can keep this fixed, rotate the other 3. Clockwise or anti-clockwise, you are going to get identical molecule. So in a Fischer group, a normal molecule, what you can do, keep one group fixed, rotate the other 3. That is what we are calling 3-group interchange, and it will, both the molecule, initial molecule and final molecule will be same. You can rotate them clockwise, you can rotate them anti-clockwise, you can rotate them 1 time, 2 time, 10 times. It doesn't matter, you are going to get the same molecule. Because 3-group rotation is like rotating the molecule, that's it. It won't change the configuration. Now let us understand few more points. Fischer projection should not be flipped out of the plane of the paper. That is not allowed. Why? Suppose this is the molecule. If the Fischer projection of this molecule is this. If I am flipping the molecule out of the plane of the paper, this is flipping the molecule out of the plane of the paper, then it loses the meaning. Why it loses the meaning? In Fischer projection, whatever groups are horizontal, that means they are outside the plane of the board. Whatever groups that are vertical are into the plane of the board. But now what we are seeing is reverse. Whatever groups, the Fischer projection of this will be, these two will be in vertical line, but they have come outside. In the Fischer projection, these two are on horizontal line, but they have gone inside. So the Fischer projection has lost its meaning. That means you can't take a Fischer projection and flip it outside completely. If you do that, it is not the identical Fischer projection. Why is this happening? Because this is a 2D representation, don't forget that. So Fischer projection, you can't flip out. When you flip out, you are changing it in 3D direction. When you are just rotating like this, the Fischer projection, you are changing in the same plane. So that keeps groups outside as outside, groups inside as inside. But when you change the Fischer projection like this, groups outside will become inside, groups inside will become outside, and that is not allowed in Fischer projection. So that is the first point. Now Fischer projection should not be rotated by 90 degree. Automatically it is same. What is a 90 degree rotation? 90 degree rotation means it's like a 2-group interchange. 90 degree rotation means keeping this hydrogen here and keeping this iron here. But that's a 2-group interchange. 90 degree rotation means after 90 degree rotation, this is going to look like this. Iodine will go here, chlorine will go here, bromine will go here, hydrogen will go here. That is a 90 degree rotation. Again, the same problem arises with 90 degree rotation. When I do a 90 degree rotation, indirectly what did I do? I brought the groups outside to inside, groups inside to outside, which is not allowed in Fischer projection. That is why you cannot do a 90 degree rotation. If you do a 90 degree rotation, configuration is going to change. D might become L, L might become D. So you are not representing the identical molecule. Next, 2-group interchange is not allowed. I just said 2-group interchange is like 90 degree rotation. If you do a 2-group interchange, that's a problem. So when I do a 2-group interchange, I can do even number of 2-group interchanges. That is, I can exchange these two, then I can exchange these two. That's an even number of 2-group interchange. Or if I can do an odd number of 2-group interchange. For example, odd number of 2-group interchange means I'm just exchanging only one pair of Fischer projection. That is, I'm exchanging only one pair. This is one odd number of 2-group interchange. So any 2 groups if I'm interchanging, I'm getting the enantiomer if it is only one chiral carbon atom. If I do two 2-group interchanges, again I'm getting the same molecule. This is all when there is only one chiral carbon atom. So even number of 2 group interchanges is going to give the same molecule. Odd number of 2 group interchanges is going to give its enantiomer. Simple meaning, look at this. This is H and OH. A 2 group interchange to these two is going to give its enantiomer. I'll write the enantiomer here. The enantiomer of this, how does it look like? OH and H. CH at the top, keep that in mind, and CH2OH. Now, I am changing the H and OH. That's a 2 group interchange. So what did it give? Its enantiomer. Is this same as this? Obviously no. So that is why if you do a 2 group interchange, or if you do 1 2 group interchange, this is odd number of 2 group interchange, then you are going to get the enantiomer. If I do 2 2 group interchanges, so this is 1 2 group interchange, I am changing this pair also, CH2OH I am changing to CHO, CHO I am changing to CHO. Now I have done the second 2 group interchange. Are these two same? Observe that, yes, they are same. So if I do even number of 2 group interchanges, that is 2 2 group interchange I have done this time, then I am going to get the same molecule. That is what is this point. If I do odd number of 2 group interchange, that is in the first case where I did only one exchange, then that is going to give the enantiomer. So that is why 3 group interchanges you can do anything. That is like rotating the whole molecule. 2 group interchange is different. That is why you can do only even number of 2 group interchanges but not odd number of 2 group interchanges. These are the things you have to be careful while manipulating the Fischer projections.